activity, Zurich, especially with a close collaborator, Klaus Ensling. So Professor Hongqi Xu has been a professor in Lund University for a very long time, but then he became he got the chair professor at Peking University from 2010, and the director of the Beijing Qi Laboratory for Quantum Devices at Peking University. And since 2021, Professor Hongqi Xu is the chief scientist and executive director of the Division of Quantum and Computing at Beijing Academy of Quantum Information Science. And he's a fellow of the American Physical Society, fellow of the International Physics Society of Japan, Society of Applied Physics. My personal tie to Hongqi has been collaborating on nanowire materials, and he was doing the transport and the theory. Hongqi is also one of these rare a person who has been starting as a theoretical physicist and also was leading an experimental group. So he has both. So it's a pleasure. You will speak today, Hongqi. The title is Towards Semiconductor Spin and Topological Quantum Computing. And thank you very much, and the floor is yours.
Okay. Yeah, so it's really my great pleasure to be here and to see the first time to EPFL. So this is really my first time to be here. So I'm really looking for come here. So now is as Philip said, we have long time collaborator since I think you started in 2006 or something. Yeah. So almost 20 years ago. So we started collaborating. In that time, I was doing quantum transport, especially Philip's very nice materials. It's not for electronics, but good for quantum devices. So we start collaborating. So that's why started quite a long time ago. And even today, so we publish one paper. Even today, almost. Right? It's online, but not given issue yet. Okay, so my great pleasure to be here. Also, see a lot of people here. Your formula to see how many people attending seminar is very nice. Is the content times food divided by distance squared. It's a very nice formula. I like it very much. So thank you very much for coming for this seminar. And I try to make this informal. In a way, is whenever you have questions and comment, you can just raise hand or even shout. Just say, okay, I have a question when I didn't see you. Okay, so the quantum for this spin and topological quantum computing, probably everyone knows here. I think the quantum science is very strong, some. So that I don't need to say very much. But however, since as Philip said, I'm now in affiliations with Peking University as a chair professor there and also director for lab, quantum devices lab. But also I'm working on this called Beijing Academy of Quantum Information Science. This is a very new research center, very new, established. So this center gives established, okay, some word block on top. Can I remove something? The top line maybe some word block. Yeah. So this yeah, maybe it's yeah. Sometimes I don't like use Zoom because always block something.
How do you remove this one?
Yeah, the bottom maybe better. Yeah. Right.
Okay.
Yeah, better.
Maybe just press OK on the acknowledge the message.
Oh.
Yes.
Okay, good. Yeah. Okay. So this new research institution was founded December 2017, 6 years ago. So more than 6 years ago, by Beijing City Council together with the Chinese Academy of Science and also Peking University and Tsinghua University. That's why I also have some duty to work at this new center. So and also this center is really we try to do the quantum technology for better work. That is our mission for the center. And the center, if you're working, let's see. Why doesn't this work? Okay, maybe this works now.
Yeah, this one in the middle.
Let's see which one is working. Let's see. Oh, why starting here? Why starting here? Somehow stuck. Okay.
I'm not sure why. Maybe
Yeah, maybe
but at least if
yeah.
you press that, it goes.
Okay, good. Yeah. Okay, so the some structure for this new center, I think so maybe good information for you. Nowadays, is world different university and government establish a lot of research center for quantum technology. So these centers basically they have 5 research divisions. And the quantum state of matter, that is the basic condensed matter physics, and quantum computing, the division of quantum computing. It's the largest division is in the center. I will see that later. Then we also have a person working in quantum communications, which a lot of use phone tools, work on that. So, and then we have the quantum measurement and quantum sensing. This is also very important. Finally, we have the kind of technology issues, materials, quantum materials, and devices. It's basically engineering issues they are working on. Besides this, we have supporting department or divisions for this one. Then we have the so-called division of engineers, because we do need engineers, and also we need a lot of people. So this division provide good engineers, trained engineers to this different research group. Of course, we have not as nice process lab as already I see the big room. I didn't go into it yet, but I see it's quite good processing lab and characterization lab you have here. So, but we also have small in size, and we also have a comprehensive measurement platform, which is basically in this case is transport different transport measurement platform. Also, we have Center for Industrialization R&D. So that is normally you have for this advanced research lab. So that is, as I said, is the division of quantum computing, the largest division in Buckets. So as I said, which is we have roughly around 320 or 30, depending on when you count. The research staff there include PhD student, sorry, not PhD, postdoc, and assistant professor level, associate professor level, and professor level. So we around 320 persons. And the division of this quantum computing, more than 150. So larger than half. So this largest division, so I'm the director for this division. So that is quite large, quite heavy work on this one. But it's good. It's challenging, but it's good. So this is difference. I said is if include some PhD students, we have almost 200 personnel working there. So and most important thing also today I see is most of important things the people working there is for these divisions. I'm oldest one. Everyone is very young, and the majority person is below 35 years old. So it's a very nice young research colleagues around me. So I'm happy with that. So that is roughly. So you see different positions, products we have in this one. Then we have a dozen of research group. So we come back to this research group structures. And in these centers, the division quantum computing, we're not working everything. So in the times establish this division, so I thought what we will do, we should not work everything. This is a major platform for quantum computing in the world nowadays. Even though this picture I took is 6 years old when the division started. So, but this still is a major platform. You use a photon as a quantum computing, which is very strong in the University of Science and Technology of China. Probably you read a lot of papers published in Nature. So they are working on using photon as a majority use polarization as the qubit information. So that is they do that. Of course, some also use spin. Then there is using trapped ion, neutral atom. That is you're also working here. I heard for quantum computing thing. So trapped ion. This is company working very nicely. And also in China, we have the Tsinghua University working on it, and they are also working very nicely. So, but it's also Okay, they are working on something. I believe maybe I can click the. Should I stop? Maybe.
Yes.
Okay. Oh.
Yes.
Let's join the meeting. Should I? Should I show?
Have a try.
Oh, we've been trying to record, but I guess it went away. What's the best thing to do? Just forget it, or
You can just reconnect if you want, or you can stop. And,
do you know what the meeting ID is?
okay, you can just stop. I can take this license with it.
Sorry, let me just close it, and then we can just continue. Sorry
Okay.
about that.
Okay. Yeah. Okay. So this is already next page. Oh, it's fine. So then is you also can work with donors and NV centers using that to do the quantum computing technology, and particularly for donor stuff, which I heard yesterday. So it's the Michelle Simons, University of New South Wales, she did fantastic work there. So for this stuff, of course, your NV center is another business you can do, but most of the time. NV center is for quantum sensing. It's very good for that. Then superconducting circuit, that is everyone knows. Now it's a lot of news about the superconducting quantum computer. There is a seminar quantum dot, which is basically for spin, and also topological devices. That is a major platform working on quantum computing today. And I would like to put these two together because both these topological issues using semiconductor materials, of course, in this case, you combine with the superconductor. So, and the basics is semiconductor. So normally, in my divisions, I call so we are three platform, trap arm platform, and superconducting circuit platform, and semiconductor chip platform. So these three things. And here, so your focus here is slightly emphasized. It's chip-based technology for quantum computing. That's what we are working on. So that's why we are not working purely photonic. We are not working on a lot of laser using things, but we are not means so we exclude them. Actually, so there are some group on this platform working on this laser trap or the optical trap for trapped ion technology. So this is our focus in the division of quantum computing of Beijing Academy of Quantum Information Science. Okay, so missions, so we really try to build a world-leading center for quantum computing technology. That is our mission. So this is, we need this word to get funding. You have to do the work, best work, then you get funding. So that's what we do. And with this, so our strategy already said we have three basic platforms, and of course with these three platforms we build up a different research group. So this different research group, the largest research group is the superconductor quantum computing group. We have around 65 persons, research engineers working on this platform. Then we have this all for try to use the semiconductor materials. Quantum dot, whatever, and the topological materials, as I said, is also based on semiconductor. So we try to work on with this one. The three group. Then we have trapped ion. This is three group. This 1, 2 group. This one is chip based. They really make use chip to trap ion. Then use laser to manipulate. But these two, neutral cold atom, or should be called the neutral atom better. So this is using laser manipulation. So that is. But this is a hardware. Chip, but you need some software. So we also have three groups working on software issues, starting with compiling. You know, so we always compiling operation system. It's a big group working on this one. Then we also have working. So with this one, we need to like other people access our quantum computer. So we have some persons working on cloud platform. So I will show you. Today we have 5 superconducting chip. Computer on cloud can be accessed worldwide, so you can access also to these things. If you're interested, I'll give you a web page. You just log on web page and read instructions. Then you sign in. Then you get a count. You can run our quantum computer. We have 2 large chip, which is one is 136 qubit chip. So you can run your code in our computer worldwide. We welcome you free of charge. We want to train people free of charge. Another one we're going to put on is we plan for 175 or 170 something qubit chip. Then we have the very stable one is 20 qubit chip, and then we have the 10 qubit chip. So that's very stable. But these larger ones, we need engineer working every day, need to tune every day. So maybe every day morning, so they are shut down, so engineer will tune. So this is very important to transfer our knowledge, our resource to the world, to outside the world, to try play around this quantum computer today. I mean, now this is not my main topic today, so I will not give example. I did give example when I was in Basel gave talk. Some example you can use to do some quantum computing. You can do the quantum chemistry. You can do some study the Higgs. You're using this quantum computer simulate Higgs. You can do some so business, financial issues. There's a lot of things you can try around. So there is also application group. This is basically, as I said, they are trying to use this our own supercomputer to demonstrate that you can do something. That's very good. To make quantum computer is reality, not to feel, oh, this is something, the future things, I never see them. But this you can really do something. So that is our duty to educate people to work on this quantum technology. That is essential thing. Okay, I thought I deleted the Chinese word, but maybe I hope up is the right one. Okay, so this is today's. Now I think maybe I use different output, different. This is one time. Okay, doesn't matter. So okay, I think I maybe have another version. So probably they are same. I hope so. I add on something. Okay, so come back to this. I really talk about this semiconductor-based quantum computing technology. So that is so-called semiconductor spin and topological quantum computing. That's what we work on. So besides these technology issues, why I'm working on this? I like this subject very well. Besides technology, there are very good physics inside. So there are a lot of fundamental physics, which is not like superconducting quantum computing technology, which is they are almost past basic science issue. Left today is engineer issue, most of that. I don't mean that there is left some of the fundamental science issue, but the majority issue is engineer issue. So that's why IBM, Google, all these big companies can jump in immediately. But for semiconductor things, it's a lot of basic science we still have not solved out. So big companies, so they are slightly so careful with put a lot of money on that. So that is leave room to us to do research, still working on fundamental science and develop technology. In terms of fundamental physics, in this side, there's a lot of many-body problem. So spin interaction is a many-body problem. There's a lot of them. And this many-body problem also interact with the contact and the gate, whatsoever. So you have a lot of strong correlation problem. You can change interaction, you have exchange gate, you change interaction, and they can manipulate by microwave, which is a boson phase. So there are a lot of many-body problem inside this one. Of course, someone also use the phonons to manipulate this spin state. So this is quite good. Of course, with this one, you also very easy to build structure to do quantum simulation. So that is a very nice system to work with, a lot of physics inside. But this one, everyone knows this topological issue is very tough. One of the most important things is non-abelian statistics. So unless we demonstrate non-abelian statistics, we not dare say we say Majorana, for example. Majorana obey non-abelian statistics. You have to demonstrate this topological state. We really show non-abelian statistics. So this is hard physics. So which is require us put a lot of effort to work on that. Then of course in this when we say the Majorana fermions, the topological state, they are protected by topology. However, if they're fully protected, that's not useful. You cannot interact with them. You don't know what they are doing. You cannot give the initial conditions, let them do quantum computing and read up. So we need to find a way to see how they couple with the fermions normally our computer, we read out, we normally using forming state. So we need to understand this one before we can do something and can be useful. Otherwise, just purely theoretical, we don't know what they are doing. So these things we have to solve. Of course, there is a lot of other things, topological particle interaction with the quantum dot state. So that is issues very important. Today's people realize that you can see many people working on topological state with the quantum dot. Of course, there is spin, because they also have working on spin in the semiconductor materials. There's the yeshiva state, resonance state, and the bump states. All these things pop up. A lot of rich physics. So that's why it's a very nice material and to work with. So this is good technology, in the same time good physics. That's why keep me and keep maybe Philip and many people. It's really happy to work on this field. I hope that I can convince you. Maybe you can in the future. So even tough, you can find something to work with. So that is a good thing. Okay, so come back. So to see is quantum computing based spin first. So then I take later on we talk about the topological state. So spin state to do quantum computing, I will not go very in detail. I think that everyone knows this original proposal by Daniel Loss and Dimitrenko. This is already did in 25 years ago. I think they did, or even 26 years now. And propose we can really use spin to do quantum computing and can be scale up. That is very important. So essential things to do this one, skip this one, everyone knows we need to work on use spin coating them, and there's a lot of state in a Brock sphere. But the essential things for us, we still need these 5 criteria for making them to work for things. And most important thing today is, I think a lot of issues are already solved. Most important is to get a very good so-called operation time, and this is coherence time divided by operation time. This is quantity factor. We need coherence time as long as possible, operation time as short as possible. So that is essential things. So the quantity factors, we should be in the order of 10,000, 100,000 to be able to make them useful. Because we need enough coherent time. Within the coherent time, we make enough number of operations. So that is the essential thing. Otherwise, it doesn't work. So that is the essential thing. But other things, I think most we already demonstrated. However, there is a scale up issue still. Scale up is still, so we are struggling. I will come this in end of this part. So to solve this coherence time, one way is to really actually you need to get this high quantity factor. Essential things you need is number of operation time should be as much as possible within the coherent time. So this is coherent time, operation time. This is coherent time. T2 time is coherent time. So that is essentially thing we try to do that. And then this strategy to increase this Q factor, basically you can do 2 things. So one thing is you go to make your materials or quantum dot spin inside as long as possible, coherent time as long as possible. This is one rule. But that's why today is people talking about group 4 semiconductor quantum dot, because in the group 4 semiconductor there is isotope silicon 28 or germanium 36. There is no spin, nuclear spin in the material. So if you can group or make your quantum dot with isotope purified materials, then you take away a lot of nuclear spin. There's not, so the spin, electron spin or Hall spin, they don't influence by nuclear spin. So coherent time will be increased dramatically. This is very good. Another route is you try to use strong spin auto interaction, because strong spin auto interaction, you can use electric field driving spin. So that is another route. And in this case, 3-5 material is good. 3-5 material is good. But however, 3-5 material, there is a nuclear spin, which is shortened. So the electron spin or Hall spin. So that is 2 routes. But nowadays, to combine these 2 routes, the people think of maybe we can use use the silicon whole state or germanium whole state. The whole state normally is weakly coupled to nuclear speed. So that is a way to try to maybe do a whole state. But it's a little bit harder for indium arsenide. Can be done with the indium antimonide in the whole state. Okay, so this is a kind of devices which is fabricated over the days, over the last few years, and I will not go into the detail for that one. And essentially things for doing semiconductor spin quantum computing. So that is a few things we need to focus on in our research. First one is quantum dot, so control single electron or whole spins. That is very important things. And then so this is a few issues. I will not go into detail. I believe maybe you already have this some kind of the basic course on that. Basically, we try to build quantum dot. And the essential things. Group 4 is also there's a very nice CMOS compatible technology. That's why today's people think very much about group 4 materials. And I said 3.5 still have some advantage. So strong spin orientation. So we're still working on that. So that is an issue. So this is the materials we are working on that. And of course there is how to initiate state, how to manipulate state, how to read out spin state. That is a lot of electronics. It's a very, very advanced electronics. And Switzerland is very good. You have very good ETH. They build a lot of electronics, high-speed electronics to manipulate. And also Basel, also very good. Also, they are selling very good electronics. So you need to build a lot of electronics to fulfill this one. So which is require an advanced electrical engineer or electronic engineer also. Otherwise, we need engineer also. Okay, the field work, this is the work done over the years. We has to go through to make this quantum dot different material system. On the early stage, when I'm working in we use the indium gallium arsenide quantum well to planar structures etch the trench. Then this is very left over. Then we use the metal gate to define a dot. So you can see very nice. You can really go to very large electrons and see. This is a double dot spectrum, so maybe people understand you can go to the last electron and see to drop in one electron, either left dot, right dot, and also both electrons have dot have electrons. So this is and this is also we did this one early stage work with also Andrea Fuller. Now he working on IBM Zurich, working together. Now very integrated with a two-dimensional gas. Using two-dimensional gas as a sensor for quantum dot here. So that is also we work on that one. And this work basically using Philip good materials, indium antimonide nanovires. So we can build quantum dot by two sources. This is indium antimonide, very beautiful indium antimonide nanovires. So we can build one quantum dot here. Then we have backgate. Then we can really map out state and also spins. So this is a different state. Hook up. Magnified, they are split, so they can split. Then we see a lot of black stripe somewhere, and then this black stripe is a conduit effect. So I will not go into more detail. And the most important things here is not conduit effect. We see so-called correlation suppression conductance. Conduit effect is correlation induced conductance. So we also see some here. Essential things, there is a conduit correlation, but there are suppression conductance. So I will go there slightly. So maybe that's a long time of work we publish. And this is indium arsenide nanomers we grew in China. And this work done at Peking University. So we can use a lot of finger gate. Each of them's finger gate is 20 nanometer in width. And pitch is around 50 nanometer or 60 nanometer. So it's very fine technology we are working with. To define several quantum dot and plunge gate on this stuff. So this is just a few examples. So this I just said is very nice. We can use two-dimensional gas. In this case, indium gallium arsenide quantum well to define a double quantum dot. See very nice spectrum. And this device there is a sensor. This is a controller. This is a sensor. This is QSE quantum pump contact. So you can see this direct measurement current passing through to see spectral. This is sensing spectral, which is the most sensitive. That is essentially we need a sensor in this technology. So we obviously need a sensor technology. This is for double dot spectral, and even with the sensor we can go to last electron. If you without sensor, when you go to this side, the current is very weak. You don't see any spectral, anything. But with sensor, you really can go to last electron and see that. So that is a very essential thing. And we need last electron, few electron, to do better quantum computing. This is one I show again. So you see the Coulomb blockade effects. This is 0 electron, 1 electron, 2 electron, and 3, 4 electron. Here is condo P. So very, in the Coulomb blockade regime, there's a very bright stripe as 0 bias. That's condo P. And with the MAGFET, if you set up the 0 bias, then as I said, this line is split. So that is due to spin. And this distance is charge energy. So which you can map out a lot of things. And with this one, you can map out charge energy. And this we call addition energy, means the charge energy plus condensation energy. If you subtract background, that means left over is charge energy. So really you can see for that. And also from this splitting, move up, subtract this charge energy, you can get G factor. So these materials, different levels have different G factor, which is around 30 to 50 or 70. It's a very large G factor. This Indian material is a very nice material to do quantum devices. Okay, as I said, is when we look at this one, this also has condo effect. The condo effect here, this is because called orbital condo. Is 0 MAGFET is spin half condo. This is orbital condo called integer spin condo. So I will not go into that. But with this one, also you can show that there is an anti-cross. The anti-cross, why is the anti-cross? Because spin orbital interaction. So we can use two model, very simple model, two-level model to figure out what's strong, what the spin orbital interaction is. So then really can, you fit in the data, you get spin orbital strength of spin orbital interaction, which is we need to know how to manipulate this state. So this is we need to. But this is probably too much in detail. This is condo peak here. So condo peak here, so you can see with the MAGFET, condo, normally you use a degenerate state. You can be state like this one, and can be also like state working this one in this level. But with the MAGFET, there is split. So condo disappeared. So this MAGFET, the final MAGFET, you see the 0 bias peak becomes split. So that is essential things. And with this width of 0 MAGFET, you can get a condo temperature. So people say, how I know condo temperature? By this one you can know that. Okay, as I said, there is a correlation in this part. Because we see the condo's spins degeneracy, but this time all spin along this degenerate point, single particle degenerate point, is same spin. They don't have flip process. And the condo you need electron jump in the condo dot. First you have condo dot say spin like this one, then next come in pick up this one. Then another one like they kick out this one. This is you need a spin flip process, but this don't have this one. But in this case, it still have correlation, but this correlation gives a suppression conductance. So in fact, I will not go here in detail. We see a lot of condo in general case, but in this case, so in this point, this is have condo because the spin is a flip process. But here, from this side, all same spin. So in this case, so it really is actually here, you don't see strap. This is condo strap, this is slightly weak condo strap, but here is nothing there. So which is essentially correlation and suppression conductance. This is new physics. So a lot of things like this one. Okay, so we move on. So we need this for single particle for single quantum dot issues. Then we have to work on double dot, triple dot, and even more to do these things. And the system become complicated. So this device we are working on in Beijing, so we can define, say, triple dot, double dot, or triple dot. So I mean, by this finger gate in this way, so we can really use this finger as a boundary gate and these two gates as a barrier gate, for example. So I will not go into detail. So and we can work on this. We can really hook up to understand, spin orbital interaction. there is two terms in spin-on detection. One is called Rashba type spin-on detection, another one is threshold. And with this device, we really can to extract both effects separately. This is also issue. And this one depends on crystal structure, but this one we can manipulate with electric field. This is we need. So this one we can manipulate with electric field, but this one is when the crystal structure fixed, there you cannot do very much about that. So we need to know how much is this term. So that is why. So we can measure this really dimensional, three-dimensional this string spin-on detection. Then we can. This one is a fixed direction basically, but this one is you rotate them. So basically you can find where your strong spin-on detection is. From this formula, you can see this Rashba type. They give the so-called effect B field as a spin-on detection. This field is perpendicular to the electric field and perpendicular to the key. K vector means it's transport propagation. So if electric field normally we know we have back electric field normally is this way, and propagation is this way. So this field normally is in implant in somehow majority, unless your electric field is different. So we can map out this one. So let's measure this angle. Then we found this one. That is essential things. Okay, so I will not go into details. So a lot of work we done. This recent work we can also work on the triple dot, quadruple dot, and or even 5 dot together. So couple 5 dots. So this is a very nice technology we work with, and spectral become complicated. I will not go into detail. And this is a basic can do the quantum simulation for molecules. Basic is a kind of molecule simulation. So that was I said we can do that. And one example for this 3 dot spectrum. If you really hook up a 3 dot spectrum, so each dot you can have spin up, down. So they have 2 states. Then 2 dot up, down, total is 4 states. Then you add another one up, down, total is 8 states. So that's 2 in a power n. So the 3 dots, 2 power 3 is 8 state. So we need to map up all 8 states by very fine measurement. So which is really so you can simulate the kind of molecular structures, who can build molecular structures in a way. Okay, so I will go now in details, and we also work recently in group 4. This is 3.5. As I said, group 4 is very good. They can purify it in the future. We not do yet. This purified source is very expensive, so we have to work out a lot of technology before we grow with the purified isotope purified materials. So this is group 4. We can use the NB to nanovary. So I will go back in detail. We can also grow quantum well. This is germanium quantum well, and these two are the barrier materials, which is silicon germanium barrier. This is the whole quantum well. We can also grow on the germanium layers and be very sharp interface aluminum. Actually, they have 1 or 2 layers of silicon to prevent interdiffusion. So that is so this one can be used. Aluminum semiconductor, germanium holes, very strong spin-on interaction. So we can use that for topological state measurement.
Maybe just a question on when you grow the aluminum layer. Do you grow it at room temperature or at cryogenic?
It's low temperature. We don't know how low because we don't have in this machine yet. We don't have a very good sensor for temperature, but it's below 0 Celsius. So we try to go as low as possible with nitrogen, helium nitrogen vapors circle. So and we will build a new MBE to make them better control. So this is so it's very nice. So this is basically we want to do. We want to do now. So that is very nice material. Okay, let's come back. This material is nanovary, and this nanovary how we grow now? Actually, is this nanovary we need etched ridge. First, let's silicon wafer. Then we etch the ridge. Then we get the ridge. And then we. So basically, glue some kind of silicon germanium on top, then we actually read. We reach, then we get glue buffer, silicon germanium buffer. On top of that, we start to glue the germanium vary and covered by silicon again. And the silicon, not all this done in situ. So which is get very good interface between the silicon and together with the germanium wire. And this shape cross section is a hard type, so we call it hardware. So this is a hardware technology, and they are grew very nicely. Then we can pattern with the metal, contact them with the metal on chip. We don't need, as we used to do, so when the Philip did work is upstanding wires. So when we need to pick up them, put on chip. But this one is they are not on chip, so we just directly use them. And also we can actually, I didn't show here, we can grow this direction, this 110 direction, then we can go to another equivalent 110 direction. We can make a square, connect them. And we can also, currently we are also working on, we can put a double wire, close the double wire, so which is really, you can grow these things on chip. So which is according to your design to make them. But to characterize this wires, we just make a simple phase effect transistor. And they show very nice phase effect. And you can reject mobility, phase effect mobility with this one, which is around 7,000 mobility. So it's very good and similar, almost similar as the indium antenna standing nanowire, also indium arsenide standing nanowire. Then we see very strong, weak anti-localization effect, indicate very strong spin-on protection in the wire, which is we need. So we have not extract value yet, so but we're going to do that also. So for this strong spin-on protection. And then we can make again using this our gate technology for this sample. So we contain them with, in this case, aluminum, and when we use some dielectric, and these 2 layers of finger gate. One layer is define, one layer defines barrier gate, another layer is as a plunger gate. So we can, in this case, this triple dot, then we can really manipulate with these 2 plunger gate. So that is things we can do. And this is very fresh data. We just measured last week. Things is very nice to see them. It's not differentiated yet, but you see Coulomb blockade, nice, already see them. And this device is not good enough because we, that's why we have to work more. You see a lot of charge trap. So we need to change materials for dielectric. This we use hafnium oxide, aluminum oxide as a dielectric, which is a lot of charge trap. So what's currently our colleague working, a young colleague working in the lab is to change the silicon nitride technology as a dielectric to remove charge trap. In that case, we hope we can see the better things. The double dot, we can also see the double dot spectrum. You can see very nice helicon term. And also, okay, I skip another slide. We also can apply a little large bias, see the very nice triangle. I think if you work on this, or you have educated for the course, you see the large bias, you see triangle, and you see spin blockade effect. We didn't see spin blockade effect. That's because charge noise. So that's why we try to change technology to improve dielectric. Okay, for quantum dot, as I said, I promise you, where we are now. So in 1998, starting to give concept for quantum dot spin qubit. But in 1998, you know, so superconducting spin qubit, superconducting qubit, first superconducting qubit already built by Japanese, Nakamura group. So it already by Japanese. But in the semiconductor, it's 1998, Daniel Ross, David Sensor, they proposed that we should work on semiconductor spin to build qubit. So about 10 years from first concept, take about 10 years, then people demonstrate first spin qubit. And in that time, it's a very short coherent time. It's some kind of 100 nanosecond or even shorter. So very short. But anyhow, they work. This is published in a very nice paper in the Science. So paper by Charlie Marcus and his co-workers, Jason Peta and also Liu Hove and Wade Seppen in that time. So it took another 10 years. They really had demonstrated. So they really get very nice, not a single qubit, probably get 2 qubit. So this took another 10 years to get it. Actually, they get very increases current time in 2018 or 18, 19, around this time. And in 2022, it's 3 group able to achieve double spin qubit and with a fidelity larger than 99.9%, which is large enough to so-called pass threshold to go on with further development to do the quantum computing. So that's very essential things. That is, there are 3 papers published in 2022. So this is very important 3 papers so published in that time. And in the same time, also by Japanese group, they also demonstrated they can make 3 dot to do quantum error correction, which is developed very fast. So starting very slowly and very quick development. You see, but this is demonstrated as a qubit. And technology also like this. You need very fine technology to define quantum dot to be able to do that. So this is also technology also grow that quickly develop as this one. So we are in my group in Beijing. So we are able to fabricate this quantum dot nicely, but we still slightly behind in the measurement technology. So that's why we are trying to catch up also to increase the electronics, which is we need a very nice electronic engineer to help us to build up the measurement. So this is the current stage of the semiconductor quantum dot, semiconductor spin quantum computing technology. So that's why. So this is then I quickly give something about the topological state in semiconductor superconductor hyperstructures. So this is maybe I think people also here working on topological state, and maybe you all know. So we need so-called Majorana state. We need to breeding them and really to do the quantum computing with breeding instead of so reading the spins by manipulating spin. But here computing is breaking them, breeding them. So that is I will not go into details. So this is quite challenging work, and Majorana is nanowire platform. You have the 2 end bound state. If that's topological superconducting nanowires, so you have 2 bound state, which is Majorana state. Or you have the 2-dimensional case. You confine with the superconductor with different phase, and this is the nanowires. Basically, this is 2-dimensional gas with a strong spin interaction. Then you have the nanowire. You cannot have bound state. So that is essential things which we need to work on this thing. So you see that we need semiconductor as base materials, then we need superconductor. So there is a combined semiconductor technology with superconductor technology. So which is essential things we need to develop. So this is one of my early work by Liu Hove. I think this work is still truly nice work. So it's although later on there are some work which retract in the natures, but this work is real solid work. So they see zero gravity maybe not Majorana, but it's solid data. So honest is solid data. So that was the earliest signature of Majorana. It's not that we see Majorana. And this work we did at the same time. Actually, so we did even earlier. And unfortunately, the publication came later because we struggling with the nature for 1 year. They published Science after 2 weeks submission. So we struggled 1 year without able to go through natures. Then finally we published in the Nanoletter. In that time, the editor Nanoletter somehow knew our work. They said, give it to us. We published immediately. So that's why we published Nanoletters. Philip, who was the author for this work, because we use the nanowire. So we see the zero gravity. So Majorana, so which is kind of the elusive particle. So we don't know. We don't see the Majorana in nature. The prediction should be exist in nature, but now I have to detect that. But basic physics is when Majorana when they meet each other, they destroy them or fuse. In a way, we call it fusion. And this fusion does not mean they disappear. They create particle, antiparticle. So that's why Majorana state zero energy. When they come together, they create particle, antiparticle. So this is a kind of features you see. So if you have a pure Majorana fuse, you should see the particle, antiparticle signature. So we can simulate this one also with a model, set up a model to simulate this one. So we create this piece of topological nanometers. This piece of topological nanometer, we should have one pairs Majorana here, one pairs Majorana here, and these two can interact. Interaction will fuse themselves and create so-called particle antiparticle state. So we should able to see in these systems still see this pairs Majorana and also particle state, antiparticle state, and triple peak structure. So then this one we can simulate that. I will not go into detail. So and this is basically showing that this is without interaction you see the two pairs Majorana state. With interaction, so you see particle state, antiparticle state. So three triple structure. So then we build a device to see can we see them. So we build a device. Again, similar devices, but another batch of devices, and we define very nice quantum dot in this one. Then you can tune interaction because when there's resonance, these two Majorana here and here will interact strongly. So you will see the large separation. So this is a spectral taken. You see it's very nice. This is different lines with different backgate voltage. You see this is valley, H valley, which is the superconducting gap. Then in the middle, they go through different Coulomb blockade effect. So they see the very nice sharp zero bell P, even go very long gate voltage. And this height of this one compared to background is similar, around 0.2 E square over H. But this is using grid, the current grid gave the real value. So look at the oscillation, that's true. But if subtract background, this 0.2 height is very nice. And essentially, if you look more carefully, they are more like a triple peak structure. So they all show triple peak structure. So we can characterize this triple peak structure together with Coulomb oscillation of a quantum dot. You see the width of them. You can see the defined width of them is really coincided with the Coulomb correlation. So which is prove the series right. So that is give some signature of Majorana. So also we see some signature of Majorana. Okay, this is not enough. We need to do the braiding. As I said, if we are doing braiding, you cannot definitely say you see the Majorana. So how to do braiding? So there's lots of theoretical proposal, complex structures. I will not go into in detail. This will use flux. You can build this superconductor with a different flux and with a triple junction. This is one way. Another way is using double wires as a basic unit, and you can do this one with a manipulator as a braiding structure. So essentially, since this is you see this double wire is a very nice structure. So sometimes we work on double wires. This is in collaboration with Christian Schillenberg in Basel and also University of Tokyo with Sigo Turocha. So we work together to build double wire with different structure to work on that. So and one of the things we see. Sometimes we don't see what we want to see, but we see some new physics. This is one example. In this case, we have double wires. This is a very nice double. Then we have a gate. We have two gates to tune. As in this schematic, we have double wires. We tune each of wires. Then we have contact aluminum in this case, and we want to see so if we can do the double wire for some signature topological state, but we didn't see them. Instead, we see the another correlation is called Latinger liquid correlation. So due to Latinger liquid correlation, this also predicted by Deming laws actually. So in Latinger liquid correlation, you can enhance supercurrent by this correlation. Otherwise, supercurrent goes to one wires with one value supercurrent, another one with another value supercurrent. if you put them together, you should just add on these supercurrent together. Due to liquid correlation, there is actual channel for Cooper pair passing through. So essentially, since we show these both figures, one of them you can understand. If we open only one channels, we got this supercurrent, another one we got this supercurrent. But if we open both of them, we got, it's not simple adding these two together, much larger. This is due to longitudinal liquid correlation. So we see the new physics. So that's why in the beginning I said it's a very nice system. Even we don't see what we want to see, but we can study a lot of new physics. So you should keep an open mind to study this system. Okay, this is another thing also published together with the Topological group. We also working on these materials. We see, you see, so this zero magnetic supercurrent, this width is supercurrent. But with the magnetic, you can see supercurrent enhanced, not suppressed. We know superconductor don't like magnetic, but this is enhanced supercurrent. This is due to the trap. So it's a trap in the superconductor. When there is a lot of vortices in the superconductor, when you increase the magnetic, vortices form. And this vortices is very nice. They can trap quantum particle, make remaining part purely Cooper pair. Then the Cooper pair don't influence by quantum particle any longer, so you can enhance supercurrent. So this is a very nice work. But this work gives indication for superconducting qubit community. Maybe small magnetic may help them increase coherence time. So this is why the paper is also important. Another thing we are together in a collaboration in a series with a Spanish group, the Gloria Palanito group, and the Korea group. So we are work together. We see this is in a quantum dot. If we have quantum dot, if we have superconductor, in this case we have the quantum phase transition. Normally we have here we have spin here, one quantum dot with spin here. We have zero junction. That means these two sides have zero junction. This is a strong Kondo regime. Or in a weak coupling regime, we have pi junction. So that means this structure can be have zero junction, pi junction, and sometimes we call the pi phase is double state, and zero junction case is single state. But actually, we try to think of in the original work we have said, what about in the boundary? In the boundary should exist both zero phase and pi phase. That means Cooper pair passing through have two channels. Zero phase channel and pi phase channel. In other words, if Cooper pair pass through with zero phase, or Cooper pair can also pass with pi phase, then the interference will be suppressing current. So that's what we originally want to see. We didn't see them clearly. Later on, we started the series. Actually, system is more complicated. Besides zero phase, there is called zero prior phase and prior phase, intermediate phase, and pi phase. This means intermediate phase there can be dominant by zero phase still mixed up with the pi phase, and pi prior phase is dominant with the pi phase but mixed up with zero phase. However, when this exists, there must be have discharge interference also. So we try to understand this one may give us the deep what we see here. That's what we want to study more. Maybe we see in the zero magnetic phase we have both phase discharge interference. When with the magnetic phase we remove this discharge interference, enhance supercurrent. That's what we want to see that. Actually, this is another work we just published now. Actually, this is a very long time work. You see, I will not go into detail. So this is a device structure, this schematic, this quantum dot here, we can control them, and control coupling also with the gate. And this is the condo, minus condo here, minus condo here. You see the very nice condo that follow the temperature behavior. And then we start to map up this spectrum. So you can see this is zero bias peak due to condo. So that is no question. And here also. But problem is when you fix this line and this source drain voltage and this backgate voltage fix this line, then starting in this direction, scan magnetic field. You see it's zero magnetic field. You see the very little conductance. when you increase manifold, conductance increases. If you cut line like this way, you see this dip. And this dip originally we believe is due to this zero pi phase interference effect. However, it's very hard for statistician to do to give us simulated data for that. So we're still waiting series to give us solid simulation to show it. We didn't get that. So that's why. And of course we can in same time we can interpret this device with a flux. So with the vortices in the superconductor trapping effect. So that's why. Since we have waiting this paper for Siri to help us for many years, but we didn't get that. We published data. We give the possibility either due to the trapping effects, either due to interference effect. So that is we just published the paper now. So I think this will motivate Siri to do the more computation. Okay, there is more work done on these things, so I will probably go quickly. Essential things to be able to see topological state, we need to go through a lot of technology issues. This is Fraunhofer patterns interference effects with this. This is the indium antimonide non-plate. I think Philip also working on indium antimonide non-plate. This is grouped by MB, and Philip also grouped by MB also. I think also MCVD also. Yeah. So we see very nice superconductivity, and we hook up potential manifold. We can see this interference pattern and this multiple under refraction, so which is a normal state. I will quickly go through here. I think and this one I want to show that when we use aluminum niobium, when we can hook up high manifold, then the high manifold there is superconductivity, and at the same time the high manifold there is quantum Hall effect. So you can see it here. This is when the manifold you see the manifold increases, suddenly you kill superconductivity. And you see, so this fine structure due to quantum Hall effect, and you see this step here. Below this quantum Hall effect, at the same time the superconductivity. And after that, superconductivity disappears. You still see the quantum Hall fine, but you don't see superconductivity. So this is coexistence, superconductivity and quantum Hall effect is also very important. So that is work down here. And also we can work on another material, indium. This is also the indium arsenide nanoplate, or we also do indium arsenide nanoplate, also can see the same structure. I will go through it. Okay, this is the same things that we can do everything very nicely for this one. And recently we also shine microwave to the device. We call the microwave radiation experiment. Then you see so-called this step, this kind of step. So this step, at the fixed microwave, you got this step. This step called Shapiro steps. You know, the one of the features in the topological state, you need to see missing odd number Shapiro step. That's a Siri prediction. So we try to see that, we didn't see that. We see, at least this experiment didn't see that. But recent experiment, I didn't put data here. We just put on archive. We do see missing Shapiro step, but there's no topology. So we work on this field, should be very careful. But it's a lot of new physics. We really dig out new physics, but not topology, not topological state. So you can see very nice this beautiful Shapiro step structures. They plot differently. This different plot is differential this one resistance. So each of these steps we get a P. So this is the boundary of the step, basically. So you got various zero order, one integer order Shapiro step regions, and boundaries in the bright region. Okay, so as I said, we also working on not only these three fine materials, we also working on germanium quantum well. Then we grew aluminum, as you see, very beautiful structures. At the moment, we can see very nice superconductivity. But this is very preliminary data. We're going to work more on this one. And germanium is whole state, is a very strong spin on interaction, must be able to create a topological state with a superconductor. Then we can create topological superconducting state. So that is we work on. In the futures, nowadays, as I said at the beginning, is quantum dot and superconductivity is very nice. We try to combine superconductor with quantum dot to build so-called Kitaev chain model to see if you can see the more robust zero bias state or zero energy state, which is behave as a topological state. So that is the future direction we go. Okay, this is my group again, so it's a very busy slide. And we're doing two things in my group in the division of quantum computing. One is spin qubit, and one is topological qubit, all based on semiconductor. So that's why we do it. Okay, so I stop here. Thank you very much.
Thank you. Thank you, Hongqi. So, do you have questions? Yes?
I have a question about the first topics. You showed that you can make a quantum dot using the nanowires.
Yeah.
Then you can imagine that you can make a 1D chain of the qubits, but if you want to do quantum connection, you need the 2D lattices.
Yeah, right.
Is there any way to make your quantum dots based on nanowires to scale up in the 2D lattices?
Yeah, the one thing that we can, as I said, is we can define wire on chip. We can really make a pattern rich. So in a two-dimensional pattern, that's one way.
So you make the nanowires align in one direction. Then you can make.
Yeah, that's one number, but we can pattern. We make them close.
Yeah.
So we are very close. So they are capacitor coupling. So we can. That's what we can do. Another thing is we also working on this planar structure, quantum well. So that one I didn't have put on data here. Well, in that time you can pattern directly two-dimensional. So two way to work on that.
So which one is the most promising for you?
Sorry.
Which one is more promising for you?
I think to me, I think at the moment probably we should work in both ways. So we will both ways because Intel and now Intel they are not very high profile, but they are working on planar structure. So they pattern them. So one of the most successful quantum dot they built is 4x4 planar structure, which is 16 quantum dot, but not yet called 16 qubit because not demonstrated this Rabi observation whatsoever. So they can build 16 quantum dot now. And even with the 7 group, they currently also build 2x3, 6 planar structure for them. This is the probably go. And nanowires has advantage contact and design. And planar structures we know there's a lot of problems. So a lot of problems. This is a quantum wire structure just beginning. So there is barriers not too stable. There's a lot of sharp track. So we are not solved all technology issue for this planar structure yet. So that's why we all the new MBE we try to really study different layer sequence to see if we can improve the stability of the quantum dot we define. So it's a lot of work, still a lot of technology work to engineer to do. But it's so that's why we work in both directions. We don't know at the moment. Yeah.
Any other question? I have just one very general zoom out question. Like, okay, let's say you get isotopically purified silicon germanium, then you grow it like perfectly, the quantum wells and so on. What would be the remaining challenges? Because I mean, the progress definitely is not as fast as people would wish with spin-based technologies. What are the remaining problems you have?
I think still, even we get very purified, purified materials, and this guarantee we get very nice single spin coherent time, very nice long spin coherent time. But integration is the issue. So integration, how to make architecture to integrate them to dress, for in the future, as a semiconductor chip today, we have billions of transistors, and they can be dressed easily by standard classical CMOS technology. But how this can be done in these quantum dot devices, and still is the issue. So probably that is issue we need to work out. Maybe we need to see we can scale up to 10 qubit. Then we can address them clearly. Then we see how technology issue is. But one of the ways to do that is probably combine this, since they are in a CMOS chip, combines quantum piece of quantum computing chip part, then combine with classical electronics on chip. So in this way, we could reduce value.
So
you also you
for wafer bonding with the
wafer bonding is one way to do wafer bonding, but then we can combine the classical chip together with the quantum chip, then we combine them together. So superconducting nowadays they have a lot of variant done, crust down, lot of variant. When they go to say nowadays we work in 100, so almost 200 qubit. This variant is terrible. You need a very huge crust or dilution phase to able to cool down them. But that is not the way to go in the future. All these connections must be done on chip. This is an engineering issue. Still need a lot of work to do. So that is a challenge. Scaling up is really challenging. We can do quite much with increases current time, but scaling up is challenging. So likewise, we are trying to work CMOS compatible technology. We try to use CMOS knowledge, transfer them to a quantum chip.
If there are no other questions, then let us thank the speaker again.